channel Euclid Mathematics. We have started lecture series on CSIR NET SET Gate and other competitive exam. So in my today's video, I'm going to explain to you all one of the question from CSIR NET previous year question paper, which is completely based on the real analysis topic. So question it is quite easy. We just have to apply convergent divergent test to verify our options are true or not. Okay, now let's get started on today's question. First of all, I'm going to explain to you all the question, and then we'll move for a detailed understanding of our solution, each and every topic, because the question it is from the option number paper third, so maybe one or more than one options are true. Okay, now let us read the question. So in our question, we have given for n greater or equal to, we have to find out n is equal to 1 upon n log n. Okay, whether this sequence or series is convergent or divergent. Okay, now our first option says that the sequence n running from 2 to infinity is convergent. Okay, so we have to check whether it is convergent or not. Okay, first of all, we have to take n as a sequence. Now in our option second, we have to take n as a series n is equal to 2 to infinity, n is convergent. Okay, we have to apply some convergent test there. Now option number third, it says that the series n is equal to 2 to infinity, an square is convergent. Okay, and option number D, it says that the series n is equal to 2 to infinity minus 1 raised to n, an is a convergent. Okay, so let us see, we'll see each and every option in detail. We'll see how the solution look like. In our question, we have given the series an. Okay, what is the series an term given? Okay, not a series. An which is given 1 upon n log n. Okay, 1 upon n log n is given. Okay, and we have to verify whether the sequence of a an. Okay, the an term is given, and n, what is the value for n? N is greater or equal to. Okay, n is running from 2 or bigger than 2. Okay, so the n value for n is running from 2 or bigger than 2, and an is defined here n log n. Okay, and we have to check the sequence. We have to check sequence. Okay, we represent sequence as n is equal to 2 to infinity. Okay, whether this sequence is convergent or divergent. Okay, so we have to check whether it is convergent or divergent. Now let me explain the meaning for convergent here. Okay, when we say that sequence is a convergent, okay, convergent means we got the any term which land to on some fixed point. Okay, within that interval. So here we can see, if we apply limit as n tends to infinity. Okay, limit as n tends to infinity to an, if we get the finite and exist point. Okay, if we get the finite exist point over here, then we say that sequence is a converges to that particular point. Okay, sequence is a converges to that particular point, and that particular point, if it is a finite, then we say that sequence is convergent. Okay, this is applicable for the sequence. For the series, you have to check some other test. Okay, these tests are very much useful for finding whether it is convergent or divergent. Okay, now let's see the solution. Okay, so we have to check whether an is sequence of an is a convergent or divergent. Okay, so limit as n tends to infinity, what is the value for n? 1 upon n log n. Okay, 1 upon n log n. So what we will get the value for n log n? 1 upon infinity log n. Okay, 1 upon infinity log infinity. Okay, so 1 upon this term, it goes to completely infinity. Okay, so 1 upon infinity, and we know that 1 upon infinity is a 0. If when we apply limit n tends to infinity, our sequence of an, it goes to 0, but 0 is a finite point, exist. Okay, and our sequence converges to 0. That means our sequence an, which is a convergent, and it converges to 0. Okay, not to infinity. Okay, so here we can see that the sequence an, which n is equal to 2 to infinity, is a convergent sequence. Okay, this is applicable for the sequence. Okay, whenever we have sequence, we take directly that sequence to infinity. but when we have series, we apply some standard result to verify it is convergent or not. Okay, now let us see our option number B. It is depend on the series. Okay, the series n is equal to 2 to infinity is a convergent. Here we have to check series an which is convergent or not. Okay, so for checking an is convergent or not, substitute the value for an. Okay, so we have an as 1 upon n log n. Okay, that means we have to check n which is equal to 2 to infinity, series n which is equal to 2 to infinity 1 upon n log n. Okay, whether it is convergent or divergent, but it is a series, so we have to apply one standard result for finding convergent of a series or not. Okay, and whenever we have the series type n into log n, where n is greater equal 1 and n is smaller than 1. Okay, whenever we have the series of this form. Okay, when p is bigger than 1 and p is smaller than 1. That means whenever we have p strictly bigger than 1. Okay, that p strictly bigger than 1, that means the term which is getting bigger and bigger, denominator term getting bigger and bigger, and when denominator getting bigger and bigger, our terms, given logarithmic term or given rational number, it goes to 0. Okay, so if it is goes to 0, then we say that it is convergent series. It is smaller than 1, that means it is goes smaller and smaller, that term is going smaller and smaller than 1, so we will say that it is a divergent. Okay, so need to understand this test. Okay, this is very much useful here for finding the solution. Okay, so series n is equal to 2 to infinity an what we have here, 2 to infinity an 1 upon n log n. Okay, n log n to the power 1, nothing is there, that means to the power 1. Okay, and p I got it here 1. What is value for p I got the value for p is 1 over here. Okay, by using this one we can verify whether it is convergent or divergent. So here we can see p bigger, strictly bigger one, then series is convergent, but I got the value for p exactly 1, then p 1 or smaller than 1, then series is divergent. Okay, so our series n is equal to 2 to infinity an is divergent, not a convergent. Okay, so here you can see, you can apply this result over here. Okay, by using this result we say that our series is divergent. Okay, now next option is given, series n is equal to 2 to infinity an square is convergent. Okay, now let's verify for an square. As we have here an is equal to series 1 upon n log n, then an square it comes series 1 upon n square log n square. Okay, so here we can see that the value for p, which is here, when we compare with the standard result, the value for p we get here 2, and when p is equal to 2, we say that p is strictly bigger than 1, and when p is strictly bigger than 1, then we say that series is convergent. Okay, then series an square is a convergent. Okay, an square is a convergent, so our option, next option, series an square is a convergent. Okay, and option number D, it says that series minus 1 raised to n an is a convergent. Okay, now let's apply. So series here given, option D, n is equal to 1, n is equal to 2 to infinity minus 1 raised to n an is convergent. Okay, by observation you may say it is a true, because it is a alternating type series. Okay, because minus 1 raised to n can be written as minus 1 plus 1 minus 1 plus 1 this way. In the series, it is a alternating series. By using Leibniz test, we say that our series is a convergent. Okay, but let's verify how the alternating series look like. We apply detailed Leibniz test here. Okay, so minus 1 raised to n into an. Okay, now put the value for an over here, so we'll get the minus 1 raised to an. What is the value for n? 1 upon n log n. Okay, 1 upon n log n here. Now let us see how the terms look like. Okay, so it is seems like that this is alternating series. Okay, alternating series like a minus 1 plus 1 minus 1 plus 1. Okay, so whenever we have alternating series in our real analysis, we apply Leibniz test for alternating series. Okay, it is a convergent test. So this series, let us see how the series look like, how the term inside this series. When we put n is equal to 1, so we will get the minus 1, 1 upon 1 into log 1. Okay, sorry, it is not 1, it is just starting from 2, because if you're going to substitute 1, the term it goes to infinity. Okay, so n it start from 2, so 1 upon 2 log 2. Okay, so here we can see log 2 is bigger than bigger term than 0, 2 is bigger term than 0, so this term is bigger. Okay, so minus 1 square is positive 1, so plus, again put n is equal to 3, so again minus 1 into 1 upon 3 log 3. So here we can see here our denominator is increasing in every step. Okay, this increases, next denominator is again coming bigger, again third denominator is coming. So the first, if I consider first term u1, which is bigger than second term u2. Okay, because this denominator is increasing. Whenever denominator is increasing, so this plus, this minus, this plus, again this minus, like these terms coming here when we expand this series. Okay, means first term is bigger, second is smaller, third is again smaller, fourth is smaller, and so on. When we expand this series, we'll get this way. Okay, the term which is a decreasing. So we got the decreasing sequence over here, sequence of a term u1, u2, u3, u4, and so on. Okay, and whenever we apply limit n tends to infinity to an, okay, 1 upon limit n tends to infinity, n log n, okay, we'll get the 1 upon infinity, which is a 0. Okay, so these two condition hold. If these two condition hold, then we can apply Leibniz test for alternating convergence of a test. Okay, and Leibniz test for series of alternating convergence test, what it says that Leibniz test for convergence. So this is applicable for alternating series. Okay, what is mean by alternating series? Alternating series means first term positive, second term negative, third term positive, fourth term negative, like this alternating series. Okay, so Leibniz test for alternating series, it says that when we have series like u1 minus u2 plus u3 minus u4 plus so on. Okay, when we have series this way. Okay, when we have series in this following way, so plus minus, and it is having following condition. Okay, so u1 need to bigger than u2, u2 need to bigger than u3, u3 need to bigger than u4, and so on. Okay, this term need to comes here. Okay, u1 need to bigger than u2, u2 need to bigger than u3, u3 need to bigger than u4. Okay, and so on. And second condition, when we apply limit as n tends to infinity un, okay, the series which is here un, when we apply limit n tends to infinity, we need to get it 0. Okay, so when these two conditions happen here, then we say that Leibniz test for alternating convergence series gives un as a convergent. Then we say that un is convergent. Okay, un is a, then we say that un is a convergent. Okay, now let's apply this term here. Okay, so limit n tends to infinity an 0. Okay, so u1 bigger than u2, u2 bigger than u3, u3 bigger than u4. Okay, so these terms are also happening here. Series is alternating positive, negative, and so on. So if these all conditions are possible here in our option D, then we say that our option D for alternating series of a convergence test by using Leibniz test, we say that minus 1 raised to n, an is a convergent. Okay, it's very easy and useful test that I hope you all have understood. Now let us see here, it is my solution, complete solution of my example. Okay, so here option first, it is a true here, option B wrong here, option C which is a true here, and option D is also true. Why it is true? Let us see the solution in our next step. Okay, so here an it is here, an plus 1 it is here, how the terms are coming. So here in my solution, next term it look like an plus 1 is smaller than an, that I already explained in my earlier part. Okay, how that series look like. Then when we apply limit n tends to infinity, we get the 0. And Leibniz test, it is here, very famous test, useful everywhere in real analysis. Okay, so u1 minus u2 plus u3 minus so on. Okay, u2 is smaller than un, and limit n tends to infinity, when we apply to un, you will get the 0. Okay, so if it is 0, then we say that series is convergent. Okay, series is convergent by using Leibniz test. Okay, by applying Leibniz test for alternating series, we say that minus 1 raised to n an is a convergent. Okay, so by using these two terms, I hope you all have understood my today's example. It is completely based on the convergence of a test for alternating series. A very easy example. It is for 4.75 marks. That means it gives us 4.75 marks very easily. Nothing is difficult here. Okay, so I hope you all understood my today's lecture. It is very easy and easy to solve. Even after, if you found anything difficult, let me know in comment section. I will come up with some other videos. So thank you everyone. Thank you for my today's lecture.